Calculus class. Today we are going to look at topic 55, vectors in two dimensions. So let's first look at vectors versus scalars. So a vector is a quantity or measurement that has both magnitude and a directional component. Whereas a scalar is a quantity or measurement that has only magnitude and no directional component. So vector values include displacement, velocity, acceleration, force, and work. Whereas scalar values would include speed, distance, temperature, and and energy. Direction counts in all of these measurements for the vector values. So let's look at an example. Let's look at displacement, which is a vector, versus distance, which is a scalar. So here we have Lake Tranquility, and we want to get from point A to point B. If we follow the road around the lake, our direction is always changing. There is no specific direction. The distance traveled on the road is a scalar quantity. So if we were to go from point A to point B using this path, our direction always changes, but we have a total distance. So that is a scalar. Now, if we were to travel along the straight line between A and B, this is the displacement, which has a specific direction and is therefore a vector. So if we were to travel from point A to point B along this straight line, we never change direction. We are going in one direction. So that is a vector. So what is magnitude? Magnitude is of a quantity that is the size or length of the quantity. Magnitude can be measured in multiple different ways depending on what is being measured. So for displacement, we have meters, feet, miles, inches, millimeters, etc. For velocity, we have meters per second, miles per minute, etc. Force would include newtons or pounds. Time includes seconds, hours, days. Temperature would include degrees Fahrenheit, degrees Celsius, kelvins. And the directional component of a vector is the direction of the vector. Direction can be measured in terms of degrees or radians, positive or negative, left, right, up or down, north, south, east, or west. So let's look at some vector notation. Vectors are written in bold letters, such as this V, or by placing an arrow above the letter, such as this example. Usually in textbooks, you're going to see, or on tests, you'll see the bold, so that means a vector. But usually when you are writing it on your paper, you're going to want to use the letter with the arrow above it. The magnitude of a vector is written with either symbols, so it kind of looks like the absolute value, but what's inside of it is the vector symbol, so the bold V or the V with the arrow over it. Or you'll see the magnitude written with double lines. Geometrically, vectors are like directed line segments or rays. Each vector has an initial point and a terminal point. So here's our vector V, and we say that the initial point, which could be called the tail or the dot, would be P, and the terminal point, which is the tip or the arrow, would be Q. The vector components. So in the two-dimensional rectangular coordinate system, we will typically place the initial point of a vector, for this example A, at the origin. This means that the terminal point of A has the coordinate A1, A2. These coordinates are called the components of A, and we write it as such. So we say that vector A has components a sub 1 and a sub 2. We use these little brackets rather than the parentheses when we're talking about normal coordinates. So a sub 1 comma a sub 2 means that the displacement of the initial point by moving a sub 1 units horizontally and a sub 2 units vertically. So this is our horizontal displacement, and this is our vertical displacement. And we call this vector the position vector. And a side note, if vectors have the same length and the same direction, even though their position is different, then we say that the vectors are equivalent or equal. The 0 vector has 0 length and no specific direction. All right, so let's look at an example. All of the vectors shown are all equivalent to the vector OP. So here is vector OP right here, starting at the origin, and we moved 3 units horizontally and 2 units vertically, and whose terminal point is at P, which is 3, 2. And if you notice, all of these vectors have the exact same length. So if you notice, we moved 3 horizontally and 2 up for every single one of them, and they're all going in the same direction. So all these vectors are equivalent because each terminal point can be reached by displacing the initial point 3 units to the right and 2 units upward. Side note, we can think of all of these geometric vectors as representations of the algebraic vector A, which is represented as 3, 2. So let's look at a general case. So we have our position vector, OP, and that means our general vector A is given by a sub 1, a sub 2. We're going to let ray AB be another representation of vector A, where the initial point is A, which is x1, y1, and the terminal point be B, which is x sub 2, y sub 2. Therefore, we must have that x sub 2 is equal to x sub 1 plus a sub 1, and y sub 2 is equal to y sub 1 plus a sub 2. And if we wanted to solve, that means that for a sub 1 would equal x sub 2 minus x sub 1, and a sub 2 would equal y sub 2 minus y sub 1. So this gives us a theorem that says that the given points A, which is represented by x, 1, y, or x sub 1, y sub 1, and B, which is x sub 2, y sub 2, the vector A with representation of ray AB can be described as x sub 2 minus x sub 1, y sub 2 minus y sub 1. So let's look at vector addition. So if vectors u and v are vectors positioned so the initial point of v is at the terminal point of u, then the sum u plus v is the vector from the initial point of u to the terminal point of v. So there are 2 ways that we can add vectors. The first one, which is the triangle or polygon method. So if we were to position the 2 vectors so that they are tail to tip without changing their direction or magnitude. So notice how I put vector u, and then vector v is sitting on the tip of vector u, and notice that their direction and magnitude is the same. The vector between the tip of u and the tail of v is the sum of u plus v, which forms a triangle. Algebraically, we can say that if vector A is given by a sub 1, a sub 2, so here's vector A, and vector B is given by b sub 1, b sub 2, here's vector B, then we can say that vector A plus B is given by A sub 1 plus B sub 1, comma A sub 2 plus B sub 2. So basically, we're adding the horizontal components together and we're adding the vertical components together. Now, the parallelogram method is that if we were to position the two vectors so that they are tip to tip, so it will look like this without changing their magnitude or direction. Copy U and V so that you have a parallelogram. So notice how I copied U, so it's parallel to itself, and I copied V, so it's also parallel to itself. The sum, this time, the sum of U plus V forms the diagonal of the parallelogram. So it would be the value from this point to this point. So scalar multiplication. If C is a scalar and V is a vector, then the scalar multiple, C times V, is the vector whose length is the magnitude of C, or sorry, the absolute value of C, times the length of V, and whose direction is the same as V if C is greater than 0, and is opposite to V if C is less than 0. If C is equal to 0, or vector V is equal to the 0 vector, then C times V is equal to 0. So let's look at an example. So 2 times V means that you have a vector that is twice as long as vector V. So here's vector V, and here's 2 times V. Basically, I copied V on top of itself. Now, if I was to have negative V equal to, which is the same thing as negative 1 times V, has the same length as V, but points in the opposite direction. We call it the negative of V. So here's V, and basically negative V has the same magnitude, it just is going in the opposite direction. Note, if we have negative 2V, that means that you have a vector that is twice as long as vector V and is pointing in the opposite direction. Algebraically, we can say that if vector A, given by A sub 1, A sub 2, and C is a scalar, then C times vector A is given by C times the horizontal component, comma, C times the vertical component. So vector subtraction. Vector subtraction is a combination of vector addition and scalar multiplication with the negative vector. So we can now say that the difference of vector U minus vector V of two vectors means it's the same thing as taking vector U and adding the negative vector of V. Geometrically, this will look like something like this. So here we have vector U and vector V. So therefore, if I was to add U and the negative vector of V, I would be going in this direction. So this is our triangle method. Now, if I was looking at the parallelogram method, we would have U and V coming off of the same point, and we would copy U and we would copy V so that they are parallel to itself. But this time, since we want negative V, we're going in the opposite direction. Algebraically, we can say that if A is represented by A sub 1, A sub 2, and B is represented by B sub 1, B sub 2, then it's the same idea as subtracting the horizontal components and subtracting the vertical components. Magnitude. We can compute the magnitude or length of a vector, A, by using the Pythagorean theorem or the distance formula. So if we look at our typical example of vector A, we have a horizontal component, which was represented by A sub 1, and then we have a vertical component, which is represented by A sub 2. Now the length of the vector of A, so I want this distance right here. And if you notice, I formed a lovely right triangle when I put the horizontal vector and the vertical vector on. I can use the Pythagorean theorem to find the magnitude, or the length. So when I do a sub 1 squared plus a sub 2 squared would have to equal a squared, and solve, I would get the following. And since magnitude represents length, it has to be positive. So hence the positive square root of a sub 1 squared plus a sub 2 squared. Now, side note that the magnitude of a vector is known as the speed of a particle along a parametric curve. So if you're ever asked to find the speed of a parametric curve using vectors, you would use the magnitude. All right, so here are some vector properties. So if A, B, and C are vectors and C and D are scalars, then we have the following properties. When you add two vectors together, that's the same thing as switching the order. The addition doesn't matter. When you add three of them together, it doesn't matter which order you add them in as well. When you have a vector plus the zero vector, of course that just gives you the vector. When you have a vector plus its negative vector, that gives you the zero vector. When you have a scalar multiplying the sum of two vectors, same thing as the distributive property. So you have the scalar times one vector plus the scalar times the other vector. And then the same idea here, if you have two scalars multiplying a vector, you can also distribute the vector. When you have two scalars multiplied by a vector, it doesn't matter which order you multiply them in. And of course, if you have 1 times a vector, that just gives you your vector. The unit vector. So, if we have the vectors I and j, these are called the standard basis vectors because they have length 1 and point in the directions of the positive x and y axes. And they have the following components. I is represented by 1, 0. And j is represented by 0, 1. We can now write any vector A in terms of I and j. So if we have our vector A given by a sub 1, a sub 2, therefore, this would be the same thing as saying a sub 1, 0 plus 0, a sub 2. And if you notice, if I was to pull out the components, so I would have a sub 1 times 1, 0, and then plus a sub 2 times 0, 1. That's the same thing as writing that vector A is equivalent to its horizontal component times the I vector, plus the vertical component times the j vector. So for example, if we have the vector given by the components 4, -7, I can rewrite it as 4 times the I vector minus 7 times the j vector. So this leads into a unit vector, and a unit vector is a vector whose length is 1. So first off, if the vector A does not equal the zero vector, then the unit vector that has the same direction as vector A is given by the vector A divided by the magnitude of vector A. So the unit vector allows us to find the direction of the vector. In other words, the unit vector determines the position you would reach traveling 1 unit of distance in the direction of the vector if you start at some point. The unit vector allows us to do vector math without changing the length of the original vector. If we didn't use the unit vector, then we would be multiplying by some random length. All right, so let's look at an example how to find the unit vector. So we want to find the unit vector of 3i minus 5j. So first thing I need to do is find the magnitude. we know that the magnitude is represented by the square root of the horizontal component squared plus the vertical component squared. So I have 3 squared plus negative 5 squared. After simplifying, I get the square root of 34. So my unit vector is going to be my vector over my magnitude, or the same thing as multiplying by 1 over my magnitude. And using my vector properties, I can distribute the magnitude through to get the following unit vector. Well, I hope you enjoyed learning about vectors in 2 dimensions. Hopefully, some of you guys have dealt with vectors before in your physics class. And I will see you in class tomorrow. Have a good night.